Okay, let's start with some announcements. So tonight you have exam 3. Let's do the same last name procedure that we did in exam 2. So if you remember which shift you came in, first third of the alphabet was 6:15 to 6:25. If you're not in the first third of the alphabet, just stay clear of the PSA 21 door. And then the second third of the alphabet, you came between 6:25 and 6:35, and then the last third, you came between 6:35 and 6:45. Remember when you came? Just come at the same time. If your group isn't up yet, just keep clear of the entrance. Okay? And again, exam prep. So we've all found this. But I did want to point out that I've included a vocabulary words list, which is especially helpful if English is not your first language, okay? So you can prepare ahead of time and get the meanings of those words. And then there was something wrong with the blank version of quiz 8. Now that is corrected. Any questions about exam 3? Okay, and then also in exam prep, less than a week away now. Tuesday night is our final exam, which is weighted much more in the second half of the semester. Okay, so there is, you can just read the review outline. I won't talk about it, but this outlines in detail what that exam kind of covers. There's nothing on the exam that's not mentioned in that outline. So when you start your studying, you should have that outline in front of you, and everything you do should be based on what you're reading in that outline. Okay? That outline should direct you to practice problems wherever you're going to find them. Okay? And also direct you to the most important videos for you to refresh on. Okay, questions about the final exam. And that is Tuesday night in PSF 166. Is that what I said before? PSF 166, 7 p.m. 7 p.m. Yes, here we go. PSF 166, Tuesday night at 7. Questions about exam 3 or the final? So this stuff that we started Monday, all this week, is important for the final exam. Very important. So it's a good chunk of the final exam is all this new stuff. And because this is, you can argue it's the most important, we've kind of reached the pinnacle of the course, the fundamental theorem. So let's start there and refresh what we said about that. The fundamental theorem of calculus says let capital F be a function that's any antiderivative of little f. Then what does the integral from a to x little f of t dt equal? This is what the fundamental theorem says. What does it equal? Capital F of x minus capital F of a. And then if we plug a value into x, so it's like we're going to use the function for a particular value of input, say b, then the integral from a to b of f of t dt becomes capital F of b minus capital F of a. And this would calculate a net change, or an amount of accumulation, a numerical amount of accumulation. It's no longer a function anymore. It's no longer a function. It's a value. It's a net change, an amount of accumulation. Okay, so this property has enabled generations of people to do calculus exercises without understanding calculus. Okay? But we understand it. So let's go back here and talk about that. Could you write a sentence that describes exactly what that is, what that means, when I put the blue box around? You should be able to. Let's take 30 seconds and see how you do. Write down to precisely define what that thing is and means. Go, see if you can do it. Here's your chance. Get those. So I'll let you, in my view, there's four key elements there's four key elements to describing what that is. So you have a couple more seconds here while they finish up, okay? Four key elements to that. Okay, so pretend you were, so grade your own here, grade your own. See how you did on your quiz. So first and foremost, what is this thing? Just, what is it? Accumulation function, okay? First and foremost, accumulation function, okay? Represented, here's number 2, represented in open form, okay? For a quantity with a rate function f of t and a reset at a. We talked about the reset idea. We're not starting accumulating at a. We could have started accumulating at any negative number way down at the left. We're going to reset at a and get a 0 accumulation at a. So that's what this is. The accumulation function represented in open form for a quantity with a rate function f of t and a reset at x equals a. Okay, what about this side? What's that?
Accumulation at x minus 0.
Accumulation at x minus 0. Is this a value, a formula, a function, something else? What? He said it's the same thing as the other one. There's only one difference. It is. This is the accumulation function. But this now we're typically think of this as expressed in closed form. It's the same function. It's the same function. It's just open form versus closed form. Okay, so the open form, we worked for about 6 weeks near the beginning of the semester up to exam 2. We worked to build and understand that open form accumulation function. And then we found rate of change from accumulation, and that's what allows us to get this closed form accumulation from rate. So we can get the closed form representation by using the mastery test rules, but we have to think in reverse, right? So we learned all these rules that get us rate of change from accumulation. So now if we want to get closed form accumulation, we're going to use those mastery test rules, but in reverse. Does it make sense? So like 80% of the semester is about this. You see? The first third was about finding the open form accumulation, and then we did all this work with rate of change and mastery test so that we could get a closed form accumulation function, or the same function represented in closed form. Really important and powerful. Okay, anybody have a question? All right, so just a reminder about the notation. Remember that capital F B minus F of A, we can notate it this way. So any f of x is any antiderivative, and then this bar with the x equals A x equals B means exactly the same thing as what the red box says. It means plug in B, plug in A, and subtract. So you'll see this notation in web work, textbooks. I'll write it and just know that it means plug in B, plug in A, and subtract. Okay, so let's put this to work here. So here's the rate of change elevation with respect to distance. I think it's similar to something we've seen before. In feet of elevation per mile of highway for a stretch of the Colorado Highway going east of the Utah border. Okay, so this is the rate of change. So here's a graph of the change in the highway's elevation from the border as a function of the number of miles from the border. Okay, so this graph, is it an accumulation graph or a rate of change graph? Most people say accumulation. You are correct. So this is the change in highway elevation. That would be accumulation. How much it's changed since the border. So at the border, the change is 0, and then we're accumulating elevation. So this road's going uphill, right? This road's going uphill. So we want to talk about the accumulated change in elevation starting at 2 miles from the border and ending at 5 miles from the border. So we want to represent that in 2 ways. How could we represent that on the graph shown? How could we represent the accumulated change in elevation starting at mile 2 and ending at mile 5. What would that be like representing it on this accumulation function? What's that? Okay, so here's 2. Here's 5. What should I do? Yeah, so I'm going to find the elevation 2 miles, the change in elevation from the border at 2 miles, and that looks like maybe about, that's a bad line, maybe about 290. Okay, so let's estimate that to be about 290. Fair? This is 200, that's 400. So we're about 290 feet up at 2 miles, and at 5 miles, this function tells us that we're, looks like about 500. It's pretty close to 500.
You just take the latter value and subtract it.
So he wants to take, so the change in elevation starting at 2 and ending at 5 would be calculated by 500 minus 290, right? So as an estimate, I'm just kind of estimating these numbers off the y-axis. We're looking at, what is that, 210 feet of change in elevation? Did I do the math right? So remember that number, about 210 feet change in elevation starting at 2 miles from the border, ending at 5 miles from the border. Okay, now I want to represent that same value using the rate function. How can I use the rate function to represent that same value, 210 feet? You should all know how to do this. In general, what will that be? How can I use the rate function to show this change? Integral, right? From 2 to 5 of, let's just rewrite that. Okay, so that was what it would be. That would be the change in elevation from 2 to 5. And we worked all semester at how that works. Okay? All right, so there's our x. So here's that same thing. Like this notation, just forget that. Okay, so there's what we just said. But now we've actually written out what r of x is. So we could go to graphing calculator and we could have graphing calculator find this value for us because it can calculate. It has a numerical way of getting the value of this open form expression. But we don't want to do that anymore. Okay, we want something streamlined. If we want something streamlined, how can we rewrite this? So using the fundamental theorem of calculus, what do we need if we want to use the fundamental theorem and represent this in closed form? What do we need? We don't need a yawn. Okay. We need a big... We don't need a big yawn. Okay, we need an antiderivative of this. Okay, we need an antiderivative of this. Okay, and so thinking about antiderivative, first you've got a constant here times this function. So remember when we took derivatives and it was the constant multiple rule? What did the constant multiple rule say for derivatives? Just hold on to it, right? You just keep it. So in going in reverse, it's the same thing. So we can start by saying this is going to be 52.8 times. So I'll just write it one more time here. And so we got cosine x times e to the sine x plus 2 dx. So, do we know our mastery rules well enough that we can say what function would give us this as its derivative? What function would have this as its rate of change? So here's what you can do. Take a stab at it. Don't be afraid. Just take a stab at it, and then what can you do to check? Take the derivative. Okay, so there's no reason to be afraid. You don't have to get it perfect on the first try. Just take a stab at it, get something close, take the derivative and compare it to what you started with. So, but I think most of us got this one. What should it be? E to the sine x plus 2x. Good. Okay, so this was your homework, right? Stuff like this. Your homework. Take the derivative. Chain rule gives you that. 2x has a derivative of 2. So it's right. And then we can, remember, let's use our new notation here. Bar like this, from 2 to 5. Means plug in 5, plug in 2, and subtract. And that whole thing times 52.8. Did I make a mistake? What's my mistake?
No, it's
Yeah, I was about to write that down. Yeah. Are we good? Okay, so now we're going to use this. We've got closed form, which is a lot more streamlined. It's a lot more user-friendly, right? User-friendly. So that we need good technology to get a closed calculation of an open form expression, but closed form is a lot streamlined, more streamlined. So here that is again, okay? And so then what do? We plug in 5, we plug in 2, and subtract. Plug in 5, plug in 2, and subtract. And now do the math, right? Do the math. You get 548.239 minus 342.28. And what was our estimate for the change based on the graph? 210. Okay, so here it confirms that our estimate was good, and it seems like we've done it right. Okay, so that's the net change in elevation starting at mile 2 from mile 5 using the closed form accumulation function. Okay, another example. Questions on this one? So this is, now we're putting to use almost everything we've worked on all semester. And so here's another example. So a culture bacteria is in a particular dish, has an initial population of 250 cells, grows at a rate given here, 50 times e to the 0.3 t cells per day. Find the population b of t at any time t greater than 0 days. What is that referring to, number 1? What's that talking about? Find the population b of t at any time. What's that the idea of? Function, right? It's saying find the function for the population of bacteria. And they've given us the name b of t. So b of t equals. So how can I write that function down without doing any math? So we should also be able to write that function down without having to do any number crunching, derivatives, antiderivatives, nothing. We can write that function down. Okay, so we want the accumulation function for a quantity whose rate is this. What is it? Integral from 0 to t of our rate. Okay, can I use t here? So if where I'm stopping accumulating is t, that's the input to the function. I got to pick a different variable here. Doesn't matter. We'll do z. But anything else besides t will work. All right, so is this the function that I want? At t equals 0, what amount of bacteria does this give us? No, what I've written. Does it give 250? What does the 0 mean right here?
reset.
Reset. Reset, meaning the amount of accumulation at the reset will be 0. So this function gives us 0 bacteria at time equals 0. So this 0 hours means that the output b of 0 will be 0. Do we want that? No, we want at time 0, we want 250 cells. So how can I revise my b function? Yeah, just all we have to do is add 250. Remember, these accumulation functions, we can just move them up and down. It doesn't change the rate of change, right? We can shift them up or down as much as we want, and the rate of change stays the same. So now we're accumulating at that rate, and now we've assured that at time equals 0, there's 250 bacteria.
Does it matter where you add to t in the function? Could you put 250 plus
All right. So could we put the 250 inside here? Inside the integral. Can we add the 250 inside the integral? What would that do if we added 250, say, to this expression? Yeah, now your rate is always 250 higher than it was. Yeah, a plus b equals b plus a. Yeah. Yeah. So, Okay. Cool. So, but we want, again, we want the streamlined version. We want the streamlined version. What do we need to do? Find an antiderivative for this. So, mastery rules. What function has that as its derivative? What function has that as its derivative? So 50. So we just pull the 50 out. All right, so what do we need? So we're getting a derivative that's e to the something. Therefore, the original function is e to that something, right? So we could start there and we could just check it from there. Will it be the same? The derivative be what we started with? No. Chain rule would give us. So let's do it. I'm going to do it. So now I'm going to take the derivative of this kind of attempt. Okay. So in red, 50e to the 0.3z. I'm going to take the derivative of that, just like the mastery test would give me 50e to the 0.3z times chain rule times the derivative of the interior function, right, by the chain rule, 0.3. So now we look at that and we say, okay, that should have been exactly the same as what I started with here. And if it's not, I need to adjust this attempt. So how am I going to adjust this attempt? So then when I take the derivative of it, based on this, I'm going to get this. Yeah, I need to divide by this, or take 1 over this, so that they will become 1, and we'll get this. So 1 over, like that, plus, and then, so this is from, what, 0 to t, plus 250. Okay, so we just got a closed form representation, but so now let's apply what this means. So I can write it out now. So what does this mean? It means plug in t, plug in 0, and subtract. So 50. So what is 50 divided by 0.3? That's like 500 over 3. So I'm going to combine these two right here and write it as 500 over 3. So e to the negative 0.3z. No, positive. Sorry. Okay. Minus 500 over 3. Plug in 0. Okay, so here's a very common mistake that students make. They say because you're plugging in 0, it'll be 0. The accumulation will be 0. Here's a case where it's not. E to the 0 is not 0. So just because you have a 0 as one of your limits of integration doesn't mean it's going to make the function 0. So be careful, okay? Plugging 0 into this does not make it 0. You get 500 over 3 e to the 0, which is 1, right? Plus 250. So now we have, this is a closed form representation. Probably. Thank you. That should be t, but plugging t in, not z. Plugging t into the function. What's that?
Or you just plug?
Yeah, 0. 0. Right. Okay, and so then how do we find the population after 10 days? We got the population function. That's what the function does. It gives us population at any number of days, right? And that's should be very easy. Anybody have a question? Yeah.
If it asks find the change of population after 10 days, can you discard the 250 because you're not going to find an exact population, you're just finding the difference of it?
Okay, yeah. So the change in population from 0 to 10 days.
Yeah, and you would just not add 250.
That's right. Well, so yeah, you would do. Yeah, so, or you could think of it as B10 minus B0. And the B0 is 250, right? So the change in population would be final minus initial, which is the same as discarding the 250. You see that? Does that make sense? Okay. Anybody have a question? Yeah, so there's a difference between the population at 10 days and the change in population in the first 10 days. That's a different value. Okay, so B of 10, so because B of 0 is not 0. Questions on this one? Okay. Doing good. All right, so let's look at some harder ones. Harder undoing the chain rule. So similar to your homework, figuring out what the antiderivative is, but harder, okay? So let's recall the chain rule first. How do we find the derivative of a composite function? What would the derivative be? Derivative of the exterior with respect to the interior as it is. Don't change the interior, and then times the derivative of the interior, right? So now, if we're working on antiderivatives, we're thinking this way. We're thinking we're going to be given something like what's up there on the right, and we're have to figure out what the original g of f of x is. That would be the idea here of antiderivative. And in the last two examples, we already kind of did this, but they were just real simple ones. So let's look at some tougher ones, okay? So the question is, what will you focus on the left in order to recover the original accumulation function? So looking at what your goal is, this thing here, g of f of x, what will you focus on over there on the when you're given that rate function over there? What will you focus on? So our goal is to get this. So we're going to focus on A or B. Yeah, doesn't it look just like A almost? It almost looks exactly like this part. So that's what we're going to focus on. We're going to focus on that part. Okay? Because it's so close to what we're trying to get. It's so close. So what will we do then? So what will the approach be? We're going to figure out which part of our given rate function is this g prime f of x. And we want g of f of x. So what are we going to do? Take the antiderivative of interior or exterior? Exterior. And leave the interior as it is. Do you see it? So we're going to write the antiderivative of the exterior function g prime, keeping the interior f as it is. And that's almost, so but there may be some mess to clean up. So we're going to check it and then clean up the mess if we need to clean up the mess. But that's basically the idea, is just find this part and take the antiderivative of the exterior function, and you basically have, you're 90% there, okay? So let's do an example. So here's that same thing summarized again, okay? We're going to be given something like on the left, that's like a rate of change or the result of chain rule. We're trying to recover the original function. So here's an example. So what do we think? So we think, okay, this is like g prime f of x times f prime of x. The result of a chain rule derivative. And I need to recover the original g of f of x. Okay, so what do we say? We got to find this. We got to find g prime f of x. And then we know that antiderivative will be that. So, which are we going to focus on? A or B? A or B? X cubed or 8 minus x to the fourth to the fifth? Which one of those is like this? B. Okay, so let's just check that. So we've got, if that's true, then what's on the inside of that, its derivative should show up somewhere else. So 8 minus x to the fourth. What's the derivative of that? Negative 4x cubed, okay? Which is essentially the same as that. It's just off by negative 4, right? It's essentially the same as that. So that kind of confirms we're looking at the right thing here. So here's our first attempt, okay? So equals attempt number 1. Attempt number 1. What are we going to do now? So we're looking at this, and the basic form of our answer will be this. So we look at the exterior, or we do antiderivative. What's the exterior? Something to the fifth. Antiderivative of something to the fifth. You had practice in your homework. Antiderivative. Something to the sixth. Antiderivative means you'd raise the power, right? You'd raise the power of 1. Okay, so you might have a different attempt that's closer, but we'll just go with this as our first attempt, okay? Because we know this is in the ballpark. But actually, I'm not done. Why? I'm not done because I've got an improper integral here. And now we're going to represent all antiderivatives. So plus z. Okay? With no bounds on the integral, remember that means all possible antiderivatives of this function. Which means any vertical shift, right? Any constant we can add. Okay, so then let's check this first attempt. Check the first attempt. So we're going to do the derivative. Derivative is 6 times 8 minus x to the 4th to the 5th times negative 4x cubed. So what are we doing? We're taking the derivative to compare it to the original. Okay? And so then what we got? Negative 24 x cubed times 8 minus x to the 4th to the 5th. And now we've got some information to revise our first attempt and maybe so get it right on the second attempt. So here this was attempt number 1. So here's attempt number 2. What do I need to do to attempt number 1 so that if I took the derivative of it, I wouldn't have that negative 24? Right, you're going to multiply by negative 1 over 24. When you get good at this, you can do it so fast. We're taking it slow, we're doing every detail, but when you start practicing and you get good at this, you can get a lot of these on the first attempt because you'll start to see this, okay? But it's really a matter of knowing your derivatives, right? Knowing derivatives really well. Okay, so then we check it. And we won't check it, we'll just say we got it. Because we know we got it, okay? Because it'll be the same thing, but now that whole thing will be times negative 1 over 24. So the negative 24 will go away, and then we'll have that thing. Doesn't make sense. Any questions? Okay, let's try another one. I gotta make it up. I don't have one here. Oh no. Oh, that's one. That doesn't work. All right. So, does this look like this? No, it doesn't. But how could we change it to make it look like this? I trust these are all math conversations. To the? Now it's looking more like what we expect to come out of a chain rule problem, right? So when you have a fraction of functions, or like a rational function, start by changing it into the product of the numerator times 1 over the denominator, or the denominator to the negative 1, like I've done here. And now it kind of looks like it. So what are we going to focus on? We're going to focus on A or B? B. And what are we going to do in our first attempt? We're going to look at B, and we're going to take the antiderivative in the exterior. We've got G prime F. We want G of F. We've got G prime of F. We want G of F. So we're going to just focus on the exterior, do the antiderivative, leave the inside the same. Antiderivative of e to the x plus 3 to the minus 1. What do you take the derivative of that gives you 1 over something, or to the minus 1? Natural log. Natural log. Natural log of? Okay. And so we notice we have this 2 here. So we can just tack that 2 on here in the first attempt. All right, and we got plus c, because we want all such antiderivatives that work. Do the check. Derivative is 2 times 1 over e to the x plus 3 times 2 times 1 over e to the x plus 3 times what? E to the x. How do we do? Exactly the same. We're done. First attempt. Got it. Okay, so we'll have more examples like this in your homework for Friday. Any questions on this technique? Yes, Sam? What's that? Hold on a second. Where do we get it? Because we're asking, what function gives us a derivative of something to the negative 1? What function, if we took the derivative of it, would give us 1 over something, or to the negative 1? That's our natural log rule, right? Natural log of something, its derivative is 1 over that something. That's what we've got. We got 1 over something. So the antiderivative will be natural log.
So essentially we're doing like, first identifying what they need, and then obviously
Figuring out what is the highlighted.
okay, so antiderivative, and then we use derivative for that. So it's like, start the derivative and
Okay, hold on a sec. Are these math conversations, Kirk? I just thought maybe you know. What's that? Okay, pay attention. I mean, to them, to make sure that they're on task, okay? It's just, there's a lot of rumbling. If that's math, okay, that's fine with me. But if it's not, then it's distracting. Okay.
So essentially, after we identify what you just said, we're taking the antiderivative, and then we're taking the derivative of that.
The derivative is taking the derivatives to check, and we should get back what we started with.
Okay. Oh, okay. So that,
This is the check of our attempt. And in this case, we got it right in the first attempt, because when we took the derivative, we got exactly what we started with. Other questions? Yes, sir?
Yeah, it's small, but isn't it going to be e to the x plus 3x? Like that's like,
Well, okay, so what's the derivative of 2 natural log e to the x plus 3? So what's the derivative of it? Did I get the derivative right? 2 times, isn't it 1 over that something?
well, if it was plus 3, would it just be 0? 3,
So what's the derivative of ln of e to the x plus 3? What's the derivative of that? 1 over that thing, unchanged, times the derivative of the interior.
Yeah, so 1 over e to the x times e to the x, right?
No, 1 over this thing,
Okay, yeah, e to the x plus 3.
right? Times the derivative of that thing,
E to the x.
e to the x. That's it. E to the x over e to the x plus 3. See it? Okay. All right. How about more complex expressions? Let's take a look at this. So you don't want to look at this and think, what am I going to do? That's not the way you want to think about it. You want to think like we've been doing all semester. What does it mean? Break it down into its pieces and identify from the inside out, what does everything mean? Okay, so let's start with sine of 3 cosine x. What does it mean? What is it? In general, what is sine of 3 cosine x? As it is in this expression, what does it represent? Rate of change function. Okay? Then let's step out and talk about this expression. What is it? Is it an accumulation function?
It's a value.
That's an accumulation.
Or an amount of accumulation? It's an amount. It's not a function. Why? Because it's the accumulation starting at 4, ending at 7 at this rate. Right? So we're accumulating at this rate, starting at 4, ending at 7. So what I put in the blue box will give you what kind of thing? A number. a value. So now, I'm going to take the rate of change of that thing in the blue box. What will you get? You got it. What will you get? Taking the rate of change of a number, a value, a constant. 0. Do you see it? That whole thing equals 0 because that integral is an amount of accumulation. It's a net change from 4 to 7 at that rate. So of a quantity at that rate. So you're taking the derivative of a constant. 0. Okay, so let's change it up now. Same rate function. Same rate function. Now what's in the blue box? Now what's in the blue box? Function. With a reset at 4, it's going to be the accumulation of a quantity that's changing at that rate with a reset at 4 until the input, or x. And then, so this is a rate function or accumulation function? Accumulation function. How are we doing, Kirk? Are we, is it math over there? Okay. It's hard to know. I know. If you're not talking about math, please don't talk anymore. Okay, listen. Don't distract those around you. Okay, accumulation function. And now I want to take what? The derivative of the accumulation function. Which will, what do you get when you take the derivative? Rate of change. Which is? Well, this accumulation was based on this rate. And now we're taking the rate of change of that accumulation. So what we think is T? No, X, right? But we need to confirm that. We need to do the math. Okay? So let's do the math. So is this whole thing just sine of 3 cosine x? All right, let's figure that out. So we can say you could work to get a closed form antiderivative for this, but it doesn't exist. There is no function whose derivative is this. There is no function that if you follow the derivative rules, you would get that. But it doesn't mean that accumulation function doesn't exist. All right, so let's say f of x is the implied antiderivative of this. And if that's the case, then what do we have? We have d dx, just forget about that, of what? F of x minus f of 4. So this capital F, we're saying it's implied that because that's a valid rate function, there's got to be some function that accumulates and therefore is an antiderivative. It's just there's no closed form antiderivative that exists. Okay? So what is this? So it's taking the derivative of a difference. It's just the difference of the derivatives. What is the rate of change of this antiderivative? Well, this. It's where that accumulation function came from. It came from at this rate of change. So sine of what is the rate of change of that antiderivative when 4 is plugged in? So what is capital F of 4? Just a number. So the rate of change is 0. So we were right with our guess. Okay, but there are examples. We'll start with an example on Friday where you need to know this process. You can't just make that initial guess. You need to know this process. So you have to understand this process in order to solve some more complicated ones, okay? So do you follow the process? It's important. All right, cards. Cards. Okay, so because we're down to the last 2 days, if you could take these last 2 cards, we'll do a card today and a card Friday, please take these especially seriously, like it was the first time you're ever doing it, okay? So I'll put the format up.